All right, at this point, we are as confused as we could possibly be about light. Is it a wave? Is it a particle? Is it both? We've heard arguments from the particle side. We've heard arguments from the wave side. We had de Broglie bring things together and talk about how they're related to one another. But the question at this point is, how do we measure them? And what do we do to measure them? And up until this point, we weren't really concerned about the electrons and their movement so much as the fact that we could see their movement. De Broglie told us that any moving particle exhibits wave-like characteristics. And those wave-like characteristics we could actually see. Now, we can't see the individual movement of a particle, but we can see its reflected wave, and we can measure that. Now, Heisenberg is a scientist who came along, and he actually talked about how we could actually measure those electrons. And he said that it was actually impossible to take a measurement without disturbing it. Impossible to measure without disturbing. Furthermore, he stated that we can't both know the position and the velocity simultaneously. We could know one or the other, but the act of measuring it would cause the other one to be false. And the final thing that he proposed, and it's an idea that actually caused an expansion of other ideas, is that we can determine the probability of an electron being in a certain area based on its characteristics and based on its movement and based on the waves that it gives off. And that probability is what we're going to talk about further. So he talked about these probable regions to locate an electron. Not necessarily exact positions, but probable regions. And that brings us to the idea proposed by Erwin Schrödinger. Schrödinger believed that the further away from the nucleus one got, the more electrons could be housed and the more energy would be expended. Thus, the wave functions would be different further away from the nucleus. And eventually what would form as a result of these different wave functions and different movements and different velocities are these ideas of these likely regions where we might find an electron at any given point. And the term that was coined for these was orbitals. What you see on this diagram here are many, many, many orbitals. Okay, different shapes and different sizes, ranging from the very simple, the S-type orbital, to the more complex, the p orbitals, and further up. To take this idea further, to expand this picture real quick, the further away from the nucleus you got, denoted by the numbers here, here, and here, the larger and more complex the regions became. These atomic orbitals are what we're going to study throughout the rest of this unit. And these are just some example shapes. The example shape we have here is that of an s orbital. This would be a p, and this would be a d. We're going to talk about these in more depth when we start talking about where we're going to place electrons. And again, we can't see an electron. We can measure its path because it exhibits wave-like properties, and you can see that wave. Think about those planes that are way up there in the sky. Often it's difficult to see those planes, but you can see that contrail line that's laid across the sky afterwards. And this is just a big diagram of all the different atomic orbitals that do exist that we know of. This group over here, this section, these are the S's. This section over here is the P. This middle section here is the D type. And this bottom section down here, these are the F's. We'll learn about what all these things mean here shortly. You don't have to know their shapes necessarily, but what you do need to understand and know is that they're likely regions in which we can find an electron. The bigger they are, meaning the further down the periodic table we get, the more electrons can be housed there, and the higher energy that those electrons then contain. thus the different wave function that they exhibit.